we'll do a review session today. If you have questions or if you want us to solve any problem that you were not able to tackle, let me know. So what do you want us to do? نحن تقريبا عملنا كل شيء بالprevious له علاقة بالpart for the midterm. هلا if you want we can continue the correction of the problems from Germany, or if you already do not have problem with them, we can do any problem you suggest. You have any problems that you want us to do أو بكمل ال correction of these problems? طيب يلا. We'll continue to correct these problems. So last time we have done a problem, I think وصلنا على 9 مظبوط 9 أو 10 last time. مين بيتذكر؟ Guys, do you hear me? Do you hear me? عم تسمعوني شي؟
Yes, can
اوكي بس حدا بيتذكر لوين وصلنا last time بالproblems تبع Germany؟ Did we solve it 10?
Yes, يمكن I think so إنه حليناه.
Okay. طيب يلا. So let us continue with the remaining problems. In problem 11, a 45 kilogram block of ice slides down a frictionless incline 1.5 meter long and 0.91 meter in height. A worker pushes up against the ice parallel to the incline so that the block slides down at constant speed. We should find the magnitude of the worker's force and how much work is done on the block by the worker's force. So in this problem here, the idea is that let us put the given. So what we know is the mass first of the block, 45 kilograms. So the weight is equal to 450 Newton. Concerning the incline, it's frictionless. This means that no friction force. The total length of our incline is 1.5 meter in length. And we have 0. Here, when they give the length of the incline, you can consider that it's if you want the curvilinear coordinate, and is the total length measured in the curvilinear coordinate is 1.5. So this is total L equals 1.5, and the height is 0.91. Now, as I said, the worker is doing a force on the ice parallel to the incline in a way that the block will slide down at constant speed. So whenever they say that the block slides down at constant speed, this means that sum of forces equals 0. So if you want, this is dynamic equilibrium. You have motion because the velocity, you have a speed, but you don't have an acceleration. So it's equivalent to solve a static problem here, because sum of forces is equal to 0. So we need to determine what is the worker's force. This is why the first step will be to draw the free body diagram of the system. So here they didn't provide us with a figure, So we can just do the figure on our own. أنا فكرت هيدي الفيجر لها. So just we have the incline لكن because they didn't give us the figure يعني مالنا curve, it's a straight line. Okay, so it's a straight line. And the length of this straight line is 1.5. So if you want to illustrate it, it's like this. This is 1.5 meters in length. And this is the height of it. Now the force applied on the block. So they said we have a block sliding down this incline. So because they said it's a smooth surface, they didn't mention anything. They said it's a frictionless surface, so no friction. Then we only have the normal reaction and the weight. So of course, if we want to maintain the motion at constant velocity, how should be the action of the worker? They told us it's parallel to the incline, but it should be up or down. To ensure constant velocity, you don't have to have an acceleration. And already your weight has a downward projection because it will help motion of the block downward. So if you don't put any force, the block will move down. Since you want, and it will accelerate then. Since you want to impose motion at constant speed, then you should put a force but parallel to the incline as they gave you, and it should be upward. So now, according to the given, the velocity is constant. So we will apply to get what is F. We'll use the Newton law with the first law of Newton, which is sum of forces equals to 0. So we'll write first that some forces equals to 0 along x and y. So we'll decompose first along x, which is the incline. So this is our x direction. And this is y. So if we project along x, the forces along x are the projection of the weight. Now, as usual, whenever you want to project the weight, you need to know what is the angle of the incline, theta. Now, for this angle, knowing this angle, you can say that since the weight is vertical and the horizontal is doing with the incline an angle of theta, this means that the angle between the weight and the incline here is 90 minus theta. So now, when you do the projection on x, you have plus w cosine 90 minus theta or sine theta. So plus w sine theta minus the force you apply equals to 0. So your force F should be equal to F to mg sine theta. Now, in order to get theta, they gave you the dimensions of your incline. You know that the length of your incline is 1.5 and the height is 0.91. So to find sine of theta, all you have to do is to say sine of theta is 0.91, which is the opposite side over the hypotenuse, which is 1.5. So we replace sine theta by 0.91 over 1.5. Now, the second question is to find the work done by the worker on the block. Okay. So here we have several forces. We need to find first the work of the worker's force. Then we should find the work of the gravitational force and the work of the normal force. And at the end, they are asking to find what is the network on the block. Okay. So of course here you can expect what will be the network. Can you tell me what will be the network before we do any calculation? What will be the network on the block in this problem? And when you do sum of work, what will be the value of sum of work of forces in this problem? إذا بنرجع للprinciple of work and energy, we know that sum of work of forces between state 1 and state 2 is equal to the kinetic energy at state 2 minus the kinetic energy at state 1. And since we are moving at constant speed, this means KE2 equals to KE1 because we have constant speed. And this means that the total work should be 0. So the positive work of the weight, which is pulling the box downward, will be opposing the negative work of the force F, which is trying to oppose motion. So this is, if you want, constant, because V is constant, and the normal will not do any work. So if you go back to your figure, then this is the weight. This is the force F. And you have a balance between them, which will imply constant velocity, no acceleration. Now, concerning the normal, we said that, of course, because the normal is perpendicular to motion, no work. So already we can say that the work of N is equal to 0. Now, if you want to calculate the work of the weight, here they should specify for us, okay, the total distance. Since they didn't say anything, we can consider that the block is starting from the upper side, okay, to the bottom. So it's moving along the total length. So if the box start motion from here and will go to this level, and we want to find the total work of weight, then since the block is sliding down, then the total work of weight will be positive. Okay, so work of weight is plus mg times the variation in height, and since the total height of the incline is given, which is 0.91 meters, then we just have to say it's plus mg times 0.91. Now, concerning the work of F, you can directly say without any calculation that the work of F is just minus the work of weight, because sum of works is 0, and the only two forces doing work are the weight and the force F. Okay, so now all you have to do then is you can do this method, or to verify also. You can verify by saying that if I want to calculate the work of the force F, the force F is opposing motion, and it's equal. We already calculated F is equal to mg times sine of theta. Okay, and the distance of displacement, if you consider that it will move from the upper point to the lower point, then the total distance of motion is 1.5. And since this force is opposing motion, so the work will be minus mg sine theta times the total distance L, which is 1.5. And you can verify that you will obtain exactly the same result, because 1.5 sine theta is equal to the height, which is 0.91. So you can use two methods, or you do the calculation of the work of weight and work of F, and you will see that they are opposite. Or if you say, if I apply the principle of work and energy, sum of work should be 0, so the work of these forces should cancel out. Okay, any question on this problem? Let us continue with solution of other problems. In problem 12, a 60 kilogram skier starts from rest at height h, 20 meters, above the end of a ski jump ramp, and leaves the ramp at an angle of 28 degrees. Neglect the effect of air resistance and assume the ramp is frictionless. What is the maximum height of his jump above the end of the ramp? So this is a projectile motion, okay? They gave us the initial height from which the skier will start. In this problem, we are combining several chapters. First, you have the conservation of mechanical energy, and then you have the projectile. Why you need conservation of mechanical energy? Because you need to know what is the initial velocity of my skier when the projectile motion will start. So to determine V0, determine the value of V0, you need to apply conservation of mechanical energy between states here, state 1 and state 2. Okay, this will give you the value of V0, and since here you just have gravitational force which is doing work, because if you take your occupant, you have the weight and you have the normal. The normal will not do any work from 1 to 2, so you just have the work of the weight. So you can say that we have conservation of mechanical energy. Now at point 1, the kinetic energy is 0. KE1 is 0 because we start from rest. At point 2, you can consider, if I take, this is my datum line, this is my reference line. So because this is my reference line, then I can say that the gravitational potential at point 2 is equal to 0. So if I write the conservation of mechanical energy, I just have that gravitational potential energy at state 1 is equal to the kinetic energy at state 2. We have that the gravitational potential energy at state 1 is mgh because the height h is given. So you have that m times g times big H is equal to half m v0 square. So this will allow us to determine what is the velocity at this point, at this level. Now, once we find the value of velocity v0, and we know the angle theta, which is, so v0 will be equal to radical 2 gh from conservation of mechanical energy. Once we have the value of v0, knowing the angle theta equals to 28 degrees, we can find the maximum height using several methods. One of the possible method is to consider that we know the value of the range. If you memorize the formula of the range, you have that the maximum height will be at the range over 2. And you can use the equation of the parabolic path to get the value of the height. If not, another method, which is also relatively simple, is to say that at the maximum height, we have Vy is 0. So we can solve for time, the time t, to get the the time at which Vy equal to 0, and then we replace the time in the equation of y. So we say first Vy is 0, and Vy, because it's projectile motion, it's minus gt plus V0 sine theta. We set it equal to 0. We get that the time needed to reach the maximum height, t, is equal to V0 sine theta over g. Now, once we find this time needed to reach the maximum height, in order to get the value of the maximum height, we just replace now into y equation. Y is minus half gt square plus V0 sine theta t. And y0 is 0. So by replacing t by its value here, you can get y maximum, which is corresponding to the maximum height. Now, if he increased his weight by putting on a backpack, would h be would h then be greater, less, or the same? You know that from projectile motion, the mass will cancel out. Okay, the mass will not affect the value of your velocity. If you have same initial velocity and same angle, whatever is your mass, the equations will not change because the acceleration will be the same. Whatever is your mass, the acceleration is minus g. This is why if you have a different mass, this will not affect the result as long as you keep the same values for big H and for your angle theta, of course. Any question on this? Yes.
أقول كله تمام.
Okay, fine. Okay. Problem 13. A block of mass 12 kilogram is released from rest on a frictionless incline of angle 30 degrees. Below the block is a spring that can be compressed 2 centimeters by a force of 270 Newton. The block momentarily stops when it compresses the spring by 5.5 centimeters. Determine how far does the block move down the incline from its rest position to the stopping point, and what is the speed of the block just as it touches the spring. So first here, what is little bit new is instead of giving the stiffness of the spring, they gave you this sentence. They told you that your block, your spring can be compressed 2 centimeters by a force of 270 Newton. This sentence will allow you to determine K, because if you know that the force developed by a spring is equal to K delta L, instead of giving you directly the stiffness of the spring, they told you that for a certain value of delta L, so for a compression of 2 centimeters, so for delta L equal to a minus 2 centimeters or minus 0.02 meters, the compressing force is 270. When we talk about compressive force, we put it as negative, so minus 270. This means that the stiffness K of your spring is equal to 270 over 0.02 Newton meter. Okay, so this is the value of my stiffness. Instead of giving it directly, they provided me with this information. So the first step will be to find what is the stiffness of my spring. Once they give me the stiffness, the calculation becomes simple. So here they are telling me that I release the block and this block will move towards the spring, then it will compress it okay, and it will stop at a certain stage. When the system will stop, the compression of my spring is 5.5 centimeter. They want me to determine how far does the block move down the incline from its rest position to the stopping point. So what are my two states? State 1 is at rest. I know that V1 is 0. State 2 is also at rest because my block will stop. So V2 is also 0. And what I know about state 2 is that the compression of my spring delta L2 is 5.5 centimeter. So delta L2, and because it's a compression, so it's negative, is minus 5.5 centimeters. And what I want to find is the total distance traveled by my block. I want to get this distance here. Whenever you have two states, state 1, state 2, with known velocity, and you want to solve for a distance, think about work and energy. Work and energy will be the easiest approach to solve. Okay, so all you have to say is, let me apply in this problem, I can apply conservation of mechanical energy because they said that the surface is frictionless. There is no friction acting on my block. So I can just say between state 1 and state 2, where my box will stop, I can just write that kinetic energy at state 1. And here if you want, حتى اللي أهين من ال conservation of mechanical energy هو work and energy, because you don't have then to specify any datum line, and you can still apply here work and energy even if you have all forces conservative. So you can say that kinetic energy at state 1 plus the work of the weight between state 1 and 2 plus the work of the spring, because only you have the weight and the spring doing forces. The weight of the spring between states 1 and 2 equals to the kinetic energy at state 2. Now, since we start from rest, we have 0 kinetic energy at the initial state. And since the block will stop at 2, then kinetic energy at state 2 is 0. So we can deduce that in this problem, the work of the weight will oppose the work of the spring. So work of weight is minus work of spring. So let us find the expression of work of weight and work of spring, function of the distance of displacement, and then we can solve for D. Okay? To start with, the weight is doing a positive work. Why? Because I'm moving downward. Since I'm moving downward, the work of the weight will be positive. So if I want to write the expression for the work of weight, I just have to say that the work of weight will be work of weight is plus mg. Now, since the weight is not along the direction of motion, which is downward, I have to project the weight on the direction of motion. So I have to do the perpendicular, and the projection will be W sine theta, because this angle here is theta. So the projection of the weight on the incline is W sine theta, and the distance of motion along the incline is D. So the work of weight is plus mg sine theta times D. Okay, you could have also found this expression using another method. If you remember, when we derived the work of the weight, we said, what is the work of weight? If I take a vertical axis upward, if I take y positive up, then the work of weight is minus mg delta y. Okay, and here what is delta y in this problem? In this problem, delta y is the variation in vertical position. So as you go downward, as you move a distance d downward, this is d, okay? This is your distance d. You have that the angle between the incline and the horizontal is theta. So your vertical displacement, this distance here, will be d sine theta, because this angle here is theta. And this distance is d sine theta. But because you are moving down, so delta y is negative here. You are moving down and y-axis is positive up. So you replace delta y by minus d sine theta. And then you get exactly the same result, because the work of weight is minus mg delta y. So if you replace delta y by minus d sine theta, you will go back to the previous result, which is plus mg times d sine theta. So this is the work of the weight function of the distance d. Now, concerning the work of the spring, we know that the work of the spring is given by work of spring equals to half k delta L1 square, which is the initial stretching or compression of the spring at state 1, minus half k delta L2 square. Now, since at the initial state the block was here, it was not in contact with the spring was unstretched, so delta L1 is 0. While at the final state, they said that at the final state, when the block will stop, it will compress the spring by 5.5 centimeter. Please pay attention for units. Whenever you want the work in joule, K is in Newton per meter and delta L is in meter. We already found the value of K in Newton per meter. So now for delta L, just make sure to convert units. So delta L2 is 0.055 meters. And then you can calculate the negative work of the spring. Now, once you calculate this work, you say that sum of work is 0. So if we replace it to the work and energy equation, what do we get? We get m times g times sine theta times the distance d is equal to, if we take minus half k delta L squared to the other side, this should be equal to half k delta L2 squared. Everything is known except d, then we can calculate the value of d. Okay, so you replace k delta L2 mg and theta by their values, you get the value of the distance d. Any question on this problem? Okay, we still have this problem 14. A boy is initially seated on the top of a hemispherical ice mound of radius r equals to 13.8 meter. He begins to slide down the ice with a negligible initial speed. Approximate the ice as being frictionless. At what height does the boy lose contact with ice? Okay, so this problem is also a combination of several chapters. You have the boy is initially at the top of this hemisphere. So we'll treat the boy as a point. Okay. Initially, the velocity is 0. And if we take the reference line here, this is the reference line. At the initial state here at point 1, we have V1 is equal to 0, and the gravitational potential energy at point 1 is equal to plus mg times r. Now, They want us to determine at what position, at what height the boy will leave the track. Okay, do you remember when they say to use this, at which position the boy will leave the track? What will be the condition then? What is the condition to leave the hemisphere here?
Normal.
Yes, very good. Whenever you lose contact, so the normal will become equal to 0. Okay, so in this problem we have already done similar problems to this. The idea is, because I have a condition on the normal, then I can profit from this to write a Newton law along the direction of the normal, which is un. Okay, so here, because you have circular motion, think about un ut. If you want to represent your un ut vectors at this position, at position 2, at position 2 your ut vector is tangent to the path, and your un vector is directed towards the center of rotation. So this is your un. And then at this particular position, since the normal is 0, and they said no friction because you have frictionless surface, the only force is the weight. So I can relate, if you want, at this position, I can find a relation between the velocity and the angle theta where the boy will leave the track. So if I consider, because theta is unknown, I want to find it. Because to find the height, I need to get the angle for which I leave the track. So to get theta, I will write first, the first equation I can write is that sum of forces along un is equal to MAN. And because I'm dealing with normal tangential coordinates, then AN is V square over radius. So sum of n equals to m times V square over r. Now, the only force having a project, n is 0, and since the only force is the weight, I projected on un. As you can see from the figure, this angle between un and w is equal to this angle theta. They are alternating angles. So I can write plus mg cosine theta equals to mv square over r. M will cancel out. And I will relate in this way the angle theta to the velocity v at point 2. So this is a first relation. This is relation number 1 between the angle theta at which I will leave the track and the velocity of my boy. So this is relation 1. But this is not enough. I need another relation between theta and the velocity at state 2. So what we will think about now, because the only force acting on the boy is the weight, we can apply conservation of mechanical energy. So to get the second equation, we write that from conservation of mechanical energy, we have that gravitational potential energy at state 1 plus kinetic energy at state 1 is equal to the gravitational potential energy at state 2 plus kinetic energy at state 2. Now, they told me that the boy starts from rest. So KE1 is 0. I can take, as we said, this is my reference line. So at the top, my gravitational potential energy is plus mg times r. Now, at position 2, I relate the gravitational potential energy to the angle theta. This is theta. So the height at point 2 is r cosine theta. So my gravitational